Hello, everyone, and welcome to video one of statistical correlation. And you may be wondering, why is there a pirate on the title page? Well, we'll find out why in just a couple of slides. but so let's start our venture into statistical correlation. All right, and so one of the first things that we need to do here, though, is distinguish between a correlational study and statistical correlation. So you may know nothing or very little about statistical correlation, but we've talked about correlational studies before, and so this harkens back to the first week of the course or the first couple weeks of the course where we talked about study methodology in terms of distinguishing between true experiments and correlational studies, right? And so a study, in order to be a true experiment, needs to meet two criteria, and those criteria are a manipulated independent variable, right? We need to set up different experimental conditions, trying to keep everything the same between those conditions, except a little tweak. And then we need to randomly assign participants to those different conditions. And so if a study does not meet those two criteria, it is a non-experimental or correlational study. It has to do with how we collect the data. Now, statistical correlation, this is a statistical analysis. This is a tool to help understand or make sense of large quantities of information. In this case, we are assessing the relationship between two continuous variables. That is, both our independent variable and dependent variable are going to be continuous. Up to this point, our DVs have always been continuous, but our IVs have been categorical. And when we have categorical independent variables, we are assessing differences between mean scores. We're examining mean differences. And so we're not going to be talking about mean differences anymore with correlation and eventually regression. All right. All our variables now are continuous. And so here, I am now going to show you my creation of a statistical decision tree where our DV is continuous. So this is an inferential statistical decision tree when we have one continuous dependent variable. All right. And so maybe after we talk about correlation regression, if we have time, we'll talk about statistical analyses that we use when our DV is categorical. But up to this point and right now, we have one dependent variable that is continuous in nature, right? And maybe it's good at this point to refresh our memory about categorical versus continuous variables, right? Continuous variables are numeric in nature, and the order of those numbers matters, right? Categorical variables can never be numerical in nature. So all our DVs up to this point and continuing through correlation and regression are going to be continuous. They are numerical. The order of those numbers matters, right? Regardless of its bail amounts for prostitutes or how many minutes it takes you to commute to campus. Yeah. And so we've been on the right side over here in this decision tree up to this point, where we've been working with categorical independent variables. We've gone over paired and independent sample t-tests, one way between subjects and within subjects ANOVA. We've gone over factorial ANOVA, two-way between subjects ANOVA. We never went over two-way within subjects ANOVA, but heck, if you know how to interpret a within subjects one-way ANOVA, you've seen two-way between subjects ANOVA, you should be able to interpret a two-way within subjects ANOVA. All right, so we've been over here on the right side. Now we're moving to the left side, where we have continuous independent variables. All right. And so we'll be working with correlation. We'll start with correlation, simple correlation. But unfortunately, we'll never get to discuss the analyses here in the middle, where we have both categorical and continuous independent variables. So we have two independent variables. One of them is categorical, one of them is continuous, and unfortunately, we just don't have time in the class to go over those situations, because we encounter those situations actually quite often. But anyways, What is statistical correlation? So there's going to be a lot of information on the slide. So bear with me as we go through it all. All right. And so before you take a look at your results for statistical correlation, just make sure that both of your variables approximate normality, right? Continuous variables, you want to make sure your continuous variables approximate normality. So that's the only data check that you want to do before doing a statistical correlation. And so the symbol for statistical correlation is a lowercase italicized R. R. That's why we have a picture of a pirate here. a lowercase italicized R. My spouse is looking over at me, shaking their head like, oh my god. I know it's corny, but you'll remember it. When you think of a pirate, you'll think of statistical correlation for the rest of your life. Right. And so when you see a lowercase italicized r, we're looking at the bivariate relationship between two continuous variables. Bivariate, bi meaning two, right? So a bivariate relationship, the relationship between two continuous variables. Our IV is continuous, our DV is continuous. The range of R is standardized, so it ranges from -1 to +1. It's a standardized value. It can only range from -1 to +1. And you get two key pieces of information from any R value. So any R value actually gives you a lot of information about the relationship between the two variables that you're looking at. Sorry. Duchess, my bird, is with me, and she's being very talkative today. She wants some scritches and scratches. Okay, so first piece of information that we get from R is direction of the relationship. And so this has to do with the sign of the R value. So R values can be negative or they can be positive. It's possible you get an R value of 0. We'll talk about that in a second here. But if we get a negative versus positive value, what does that mean? So if we get a positive correlation, that means as values go up on one variable, they also tend to go up on the other variable. That's right, Duchess, right? Or semantically, you can say as scores on one variable go down, they also go down on the other variable, right? And we can demonstrate this in what is called a scatter plot, where we plot the values of the IV against the values of the DV, right? So, for example, for this little x, each little x represents a participant, and so this particular participant here has a score of about maybe 3 on the IV and about 2 on the DV, versus this x up here, this little x up here, this participant score is pretty high in the IV, 1, 2, 3, 4, 5, 6, 7, 8, 9 on the IV, and 1, 2, 3, 4, 5, 6, 7, 8, 9, about 8 on the DV, right? And so we plot all the participants here, and then we can draw a line through the data points. And this line is sometimes called the line of best fit, which minimizes the distances between every participant, right? And if we draw this line, it goes upward, right? So this shows that as people score higher on the IV, they tend to score higher on the DV, right? There's a positive gradient, a positive relationship. So positive correlation means the values tend to go in the same direction. For a negative correlation, a negative relationship, the values tend to go in the opposite direction. So as people tend to score higher in one variable, they tend to score lower on the other variable. And so if we draw a scatter plot of a negative correlation, the line here of best fit doesn't go upward, it goes downward, right? So as people tend to score higher on the IV, they tend to score lower on the DV. Or you can say as people tend to score lower on the IV, they tend to score higher on the DV, that the values tend to go in the opposite direction. Up, down, up. versus positive correlation, where they're going in the same direction, up, up, down, down. So that's direction. So next, let's talk about magnitude. And magnitude has to do with the absolute value of the correlation, of the R value. So we're disregarding the sign regardless of whether it's positive or negative, right? So as the R value gets bigger, as the R value gets larger, that's going to tell us about how strong the relationship is between the two variables. So as the R value gets bigger, as it gets larger, the stronger the relationship is between those two variables, right? Bigger they are, stronger the relationship. And Cohen has guidelines for interpreting R values because we've talked about magnitude before in terms of effect size. And so R, acts as an effect size because it tells us about how strong the relationship is between the two variables. And so when we get a R value that is less than 0.2, we say that that's a weak relationship. 0.2 to 0.39 is a moderate relationship. And then 0.4 or above is strong. So I know you have guidelines for interpreting a whole bunch of stuff, right? P, D, partial eta squared, and now R. And I'm sorry, it's a pain in the ass, I know, but it's just something that you have to memorize, right? So maybe to help contextualize our discussion here, to help understand R, let's talk about what an R of 0, if we get an R value of 0, what does that mean? Versus an R equal to 1, exactly equal to 1, right? So we're looking at the relationship between two continuous variables. Our IV is continuous, our DV is continuous. We run the analysis and we get an R value of 0. What does that mean? R value means that there's zero relationship, that there is no relationship, absolutely no relationship between those two variables. So if we know your score on the IV, it doesn't tell us anything about where you score on the DV. But if we get an R value of 1, exactly equal to 1, regardless of whether it's positive or negative, we get an R value of 1. What does that tell us about the relationship between the two variables? We don't have no relationship. We have a lot of people say very strong relationship. Yes, a very strong relationship. In fact, a perfect relationship. Oh crap! I forgot. Before we talk about R value of 1, just to let you know, if we get a R equal to 0, this is what the scatter plot would look like. So we would not have a line. Our line of best fit would not slope upward. It would not slope downward. It would actually be flat. We would have a flat scatter plot, a flat line in our scatter plot. So this would indicate no correlation. Correlation of equal to 0. That the data points plotted, the plotted data points do not form any pattern. So that's no relationship. An R value of 1 would be a perfect relationship, meaning that if we know your score for one variable, we can predict with 100% accuracy your score on the other. So if we know your score on the IV, we can perfectly predict where you score on the DV. And if you're like, I've heard this before, we've had a similar conversation when we talked about partial eta squared. Partial eta squared, right, is the effect size for a main effect or a simple effect in ANOVA, right? And partial eta squared also ranges from 0 to 1, right? And if we get a partial eta squared value of 1, right, that means that if we know your score on the IV, we can perfectly predict your score on the DV, and that reasoning holds here. So if you get an R value of 1, that means we have a perfect relationship. We can perfectly predict your score on the DV if we know your score on the IV. But again, we're not expecting a R value to even get close to 1. In fact, right, Cohen's guidelines specify here that if we get a correlation value, an R value of zero point 0.4, and that actually indicates a pretty strong relationship between those two variables. Okay, just coming in about 15 minutes here. So that was the introduction to statistical correlation. In the next video, we'll jump into actual SPSS output.